The next section of 4.5 deals with shifting sine and cosine curves sideways, horizontal shifts, and stretching or squeezing them in the sideways direction. So, here we go. We're going to look at some graphs again. Let's start with the graph of y equals sine x. And there's that. We saw in a previous video where if you took a parabola and replaced the x by an x minus 2, it shifted the graph 2 to the right, or an x minus 3 would shift it 2 to the right, 3 to the right. So a similar kind of thing works with any function, and sine and cosine are same as any other. So if I look at sine of x minus 2, that should take the sine curve and shift it over 2. Now let's see if we can see that that's the case. I'm going to zoom in a bit here. So here is, the black one was the original sine curve, and the blue one is the sine of x minus 2. So there's that point shifted over. The whole graph got moved over too. X minus h for any function, you replace inside the parentheses, you replace the x by x minus h, it will shift it h to the right. So x minus 1, the black is shifted 1 to the right. If I said x plus 1, so that would be x minus negative 1, then the shift goes in the other direction. The black curve got shifted over here. Now sometimes with sine curves it's hard to tell what direction they actually got shifted. Maybe that curve got shifted clear over to here. The black curve, that is, got shifted clear over to there. Well, there it would be equivalent, but the result of this x plus 1 is to shift the graph to the left 1. With quadratics, particularly with x squared, we talked about 0 playing a special role. Well, 0 is kind of a special spot as well here. I think of it as the place where the sine curve starts. The sine curve starts at the origin and heads upward. Now, the blue curve, where does it start? Well, if I think of the sine starting when you have an input of 0, well, what value of x makes this sine of x plus 1 give the sine an input of 0? Well, if x plus 1 has to equal 0, then x would be at negative 1. Negative 1 plus 1 is 0. So negative 1, x equals negative 1, is playing the role for the blue curve that x equals 0 did for the black curve. The whole graph gets shifted over that 1. Now, one of the things we didn't talk about with quadratics is scaling in the x direction. Okay. The reason we didn't talk about it is because it's hard to see on a parabola how things get scaled. For instance, let me type right here x squared. Okay. And what I want to do is I want to replace x here by 2x, or x times 2. Oh, actually, let's do it this way. Okay. Compare the red graph, which is y equals x squared, with the green graph, y equals, in parentheses, 2x squared. The x that was in this one has been replaced by a 2x. What is the result? What is the effect of the graph now? And I look at that. How does the green one compare to the red one? Now, a lot of people, when I ask that, will say, it's taller. It got stretched up. Well, I don't like to think of it that way, because what I would rather say in this case is that it got squeezed in, that the green graph is skinnier than the red graph. Yeah, it can look taller or it could look skinnier. But the thing is, what happened when you replace x by 2x is that the x's on the inputs to the square function on this one go by twice as fast as the inputs there. For instance, you get up to x equals 1 on the red graph when x is 1. The output is 1 when the input is 1. On the green graph, the output is 1 exactly half as soon. When x is a half times 2 is 1, and you get an input of 1, you square that, an output of 1. So where the red graph went through 1, 1, the green graph goes through a half 1. Same y value, the x value gets cut in half. Another place you can see that is up at 4. When does the graph get up to 4? Well, with a y value of 4, it happens with an x value of 2 on the red graph. For a y value of 4, you need an input to the square of 2. You need a 2 squared. Well, but the input to this squaring function is a 2x. So 2x would have to equal 2, x would have to equal 1. The red graph gets up to 4 when x is 2. The green graph gets up to 4 when x is 1, exactly half as big. For any point on the red graph, you can find a corresponding point halfway with the y value is the same, but the x value is cut in half. The green graph is squeezed in by a factor of 2. Now, the thing with squares is you can write this separately. You can write this differently because 2x squared is 2x times 2x, which you could rewrite if you want as 4x squared. Right? That green graph looks just like the other one did because 2x squared is 4x squared. I hope you can hear my parentheses with my pauses. This green graph, I really would say, is taller than the red graph, where the last one was skinnier. The reason is that I would say that is the 4 is now on the outside of the squaring function, where before the 2 was on the inside. When you're outside the function, you're affecting the y value. When you're inside, you're affecting the x value. So, we're going to now do this with the sine curve. And the thing with the sine curve, it's really easy to tell whether things have been stretched in the x or the y direction because the effect looks very different. Let me throw a 2 in here. This would be the sine of 2x. Okay. The black curve was the original sine x. And if I zoom this over a little bit, we can see one cycle between 0 and 2 pi. Now the sine of 2x has one cycle between 0 and pi. All the x's from the black curve have been squeezed in by a factor of 2. This isn't any taller. We didn't do anything to the y values. The black curve went up as high as 1, down as low as -1. Same with the blue, up as high as 1, down as low as -1. The thing is, the blue curve gets up and down 2 times for every time the black curve does it once. It's moving up and down faster. The inputs to the sine curve here, the sine function here, are twice as big as the inputs to the sine there. So you're getting the sine going up and down twice as fast. Well, if it's going up and down twice as fast, then the period is half as big. Where the period of the black curve was 2 pi, the period of the blue curve is only pi. So we've taken that period and cut it in half. What do you think would happen if I put a 3 here instead of a 2? That's not what I wanted. I put the 3 on the outside. Not sure why I typed it that way. Let me see if I can get rid of that. There's that. I want a 3 inside of here. Inside. There we go. Now the blue is going up and down even faster. Let's go. The black curve does one cycle from 0 to 2 pi. And in the same amount of time, the x value goes up and down once, up and down twice, up and down 3 times. There are 3 cycles of the sine curve for the blue graph, where the black one only had 1. The period has been cut in thirds. So where the black graph has a period of 2 pi, the blue graph must have a period of 2 pi over 3. After a while, we begin to see a pattern here, and there's a definite relationship between that number in there and the period. So for instance, if we have the sine of b times x, I'm going to use b because that's what the book uses right there, then the period of this graph is going to equal 2 pi divided by, select that whole thing and say divided by b. So if you're looking at the equation and you can see that it's a sine of 7x, then you can calculate that the period of this graph will be 2 pi divided by 7. Likewise, if you know what you want for a period, you can figure out what b you have to use, because just taking this equation right here and solving for b, actually let me see if I can do that. Multiply both sides by b, bring that over there. Okay. So the b got moved over, so now I have b times the period is 2 pi. And I'm going to take the period and move it over to this side. And I've got the b is equal to 2 pi divided by the period. For some reason it opted to write the 2 out in front, but it's still equal to 2 pi divided by the period. If you know b, you can find the period. Divide 2 pi by b and you get the period. If you know the period, you can find the coefficient you need, b, by taking 2 pi and divided by the period. If you got one, you can find the other. Okay. Now let's go back to this. Big numbers here shrink it. Small numbers, it turns out, will stretch it, because things, if I put in a half here rather than a 3, let's say 1 divided by 2, what's happening to the graph now? Well, where the black graph had 1 cycle, that's the regular sine curve, the blue graph has a half a cycle. It goes from 0 up to 1 and back down again. In order to get to a complete cycle of the blue one, you got to go clear out here to just over 12, maybe 12 and a half. Well, that's going to be 4 pi. Right? Let me zoom out so you can see that there's 0. There's the black graph finishing 1 cycle from 0 to 2 pi. The black graph finishes its second cycle from 0 to 4 pi. And the blue one just finished its first cycle. Okay. So with a coefficient of a half here, we have the period is equal to 4 pi. Well, does that make sense from our equation here? If b is equal to a half, do we get 4 pi? Actually, I can do this kind of substitution. Say b equals 1 divided by 2. Select that equation. Stick it in for b. And it calculates period equals 4 pi. Actually, this is kind of nifty at this point, because I can go back and change b to anything I want. B equals 2. The period is pi, right? 2 pi divided by 2. If b is equal to 3, the period is 2 pi divided by 3.